Bon, voilà, c'est prêt. Alors, c'est ici, ça se passe ici. Ouais. On peut commencer? So, hello, welcome to the eighth lecture. Yes, thank you. Last time we did two things. We started with some material on natural semantics, and then I opened a parenthesis, a big parenthesis on an advanced topic, which is inversion. So what we did was to explain something which is simpler than inversion, which is how to discriminate between values made of different constructors. Okay, so in Coq, the tactic is called discriminate. Okay, and we explained that this tactic can be explained in terms of contagious equalities. And then we move to something which is more powerful, because this is not enough to do what everything. And in particular, we started to see the inversion tactic of Coq, and to some extent explained it in terms of something. So Coq, the Coq one is not written exactly this way, but I think it's rather similar. So the point was this famous lemma called souvenir, or remembering, maybe, I'm not sure. Okay, but I think souvenir can work also in English. So that we discussed many variants for this one, but at the end we have no choice. Okay. So the idea is that, okay, when you have to prove some goal, some conclusion, eventually by reverting some hypothesis in the conclusion in order to see all the occurrences of some pilot, some argument, special arguments. So okay, the point is that you have to express your conclusion in terms of some property applied to some specific value. That in this value, the intent is to discriminate this value and this value later. And in order to do that, before performing the basic destruct, because an inversion is basically a destruct on something, we replace this goal by using this lemma by this more general goal, which basically remembers that the y, which is, how to say, attacked by the destruct, will be remembered in. So we replace this y, which could be an expression, a specific expression. Okay, I don't know. For instance, if it is a NAT, it could be a sequence of addition, multiplications, application. For instance, an expression like this. So you replace it by a variable. The point is that you will something which is finished by a variable. So we have for all x, which is a variable, but to remember that x is equal to the expression. Okay, which is important to keep somewhere. Okay, and then performing the destruct works. So at the end, you have something which is simple to prove. Okay. And so I finished this this one. Yes. Okay. Okay, so I will introduce you the example I will use in the sequel. The sequel. Oh, I think so, yes. For this one, everything is at the beginning. So remember, basically we have an enumerity type of with many colors, and green, orange, and red for only 3 of them, we have a next color. Okay, so the next you expect in everyday life. So we have this relation next color, and the point is that if I have in a hypothesis next color of a specific color and something, I would be able to say that actually only one. If I have next color of orange and something, I would say that actually only this constructor is relevant. The others should be removed intuitively. So this is what inversion does. So I will go directly to the end because we were at this point at the end. Yes, a typical. Okay, so a typical theorem is this one. Okay, if I have next color orange and some variable C2, this C2 needs to be red. Okay, so in Coq, you just write inversion. So it has go here. Okay, so time to figure. Okay, so the introductions as usual, and then here instead of destruct, which would not work on NC, I will so the standard Coq technique is just to use the tactic inversion, and the inversion will produce inversion will have two effects. It will actually enforce C2 to be red by analyzing the possible options for this hypothesis. So C2 can only be red. So you will see that C2 will be replaced by red. And as a side effect, we also keep this equality as a kind of souvenir, if you want. Okay, and then we finish by reflexivity. Okay, and the second interesting case, basic case, is when you consider a color which has no next color, such as purple. Okay, so let us introduce. Okay, so in this case, we have a hypothesis here which says basically there is no possible C2. How to proceed? So it's a little bit like discriminate, and actually, we discriminate. There is nothing to discriminate. Discriminate is for an equality. Here it is not an equality. It is something more complicated. So, but inversion still work. Okay. So in this case, we can see the technique with the explicit souvenir. So I revert the hypothesis in order to have all the formulas who talk about C2. So everything is in the conclusion part. So my property P in souvenir, so it is not this P, it is a predicate, will be it is this function, this thing seen as a function of purple. Sorry. Okay, so I could make the change by hand, but Coq has a convenient tactic. Remember, it is called pattern, which can be used in many situations. So and sometimes, in this case, there is no choice. So we have only one occurrence of purple. But by the way, I mentioned that you could have, in general, several occurrences of purple, say, in this part. You could have one here, one here, there, one in several parts. But you want to focus only on some occurrences, then pattern has possibilities, has extensions to say pattern purple at 1, 3, 5, for instance. In that case, you would say, I consider only the first, third, and fifth occurrences of purple. Okay, I don't need that today, but remember that this pattern can be useful. Okay, so let us perform this tactic. And now, so I have some predicate apply to purple, I apply the lemma, the souvenir lemma. Okay, so I get something which is equivalent, but with the point is that I have now a variable at this place here. Okay, so let us introduce to see things more clearly. Okay, actually, yes. Okay, so okay, this is simpler. So the point is that now I can do a pattern matching on the three possibilities of next color, and all of them will enforce respectively C1 to be green, orange, or red. Okay, so I will get here each time a green, orange, or red value. Okay, maybe actually it's better to see. Okay, if you want to compare, it makes sense to make E1 in the conclusion, so it's easier to see. Okay, so you see the real thing. If you write the same thing, not with the destruct here, but with a refine, you would say I refine NC, refine with pattern matching of NC, which returns all this formula. Do you want to see? So anyway, I can, okay, so, okay, I will show you first without the revert. Okay, so I discriminate, and you see that so each time E1 becomes in the place of C1, I have now green, and I can discriminate. Okay. Second one, I have an orange and can discriminate, etc. Okay. If you want to see what happens without the okay, no, sorry, with the revert here, so I can show you. So an option is to say revert E1, which will be more explicit actually. Okay. Now, if I do refine, I have to remember the name of the constructor. Refine NC. Sorry, match NC with, or I could say more explicitly return something, but I think Coq will guess it. So I have to remember the name of the constructor. So it's the bad point of refine. Okay, NCG, okay, donc NCG something, NCO, NCR, okay, and okay, I think that's okay. Okay, so you see the three goals. The revert has to be reverted itself, so I need to. I could say, and in each case, I will make an introduction of the equality. Okay, so intro, etc. So I could actually put this in the goal, by saying fun some equality. Okay. Okay. Okay, so you see exactly the same situation as before with the destruct. So you see that destruct, and remember, destruct does a lot of work. Okay, and okay, so it's basically the same. And by the way, if I forgot the revert, so it's very precise. In that case, the match will only CP. The match is very basic. The match does not do the revert by itself. So the only thing that I can do in that case, so I cannot. So there is nothing to introduce. If I try, Coq will complain. Coq will say the type is not the right one. Okay, so I need to. So you see that something wrong will happen here. Okay, so the refine, okay, just say, okay, okay, please prove P in the three cases, but nothing happened here. Okay, so this is why you need to do the revert. Okay, but in that case, okay, you have all the needed material for to continue in that case in the conclusion. Okay, here because here the type that you have here, the return type is simple, it's P. In that case, the return type is something implies P. Okay. Okay, so undo. Maybe one. And revert. Revert E1. Now it works. Okay. And now, okay, so. Okay, so I am in a painful situation. Okay, so I just instead of counting everything, I will just put this in comments. I will yes, okay. At the end. Okay, so okay, and then a more interesting use of inversion here. You see that we have to perform 2 times inversion. So here is the goal. So 4 colors: C1, C2, C3, C4. You apply next color 3 times in some sense. Okay, if you see this as a set theoretic function. Okay, and so after 3 rounds, you have C4, which should be equal to C1. So basically, you will reason by case on the first one. Next color, CS. Oh, okay, it's better to call it. CS means color suivante actually. Okay. I'll use NC, which is better here. Okay. I like to see a bottom window here. Okay. So, okay, so let us see. So I will first perform an ordinary destruct here, because there is no point to make an inversion. Actually, it would make no sense. An inversion makes sense if one of the arguments, the first in our case, is more precise. So now we have a variable. So okay, just a destruct is okay. And then we have our three cases, and now we start to wish to use our hypothesis with specific argument first as a specific values for the first argument. Okay, orange in this case, and by using in the right way this hypothesis, I will get that C3 can only be red. So C3 here will be red, and again with a red here, I need to have a green in this position, and it will be finished. Okay, so okay, so we can. So here I just use inversion. Okay, so you see that inversions tend to produce equalities, which are somewhat a little bit painful, but okay, we just clean them with a subst. Okay, inversion again. Okay, here you see the red. Okay, and okay, and at this point, I can use reflexivity, and we can also do this at once if you want to play with tactical, so combination of tactics. So here I use a sequence, a subst, and a sequence. Okay, so with one command, I can finish. Okay. So now I'll show you another technique. For some reason, let me see just a little experiment. Print next color. Sorry. Okay, so you see that Coq works a lot. Okay, for this one. And this one is not very long. I will show you another one later, which is still more interesting. Okay, so now I will go to this file, so advance 2 on small inversions. Okay. So remember, so Coq proceeds a little bit differently because Coq does not use this specific souvenir lemma, but it is roughly similar to this technique. So the point is that if you remember, I used discriminate 3 times, okay, which is a little bit annoying, especially when you have, and moreover, I introduced equalities like Coq inversion. So we'll see a technique where you don't have these drawbacks. So just a point of vocabulary. So I will call the specific argument orange, etc. The first argument, I will call it the pilot. Okay, so a kind of driving argument. And so, okay, I think that you have a little bit of explanations here. So we have this discriminate 3 times. Okay, and so what we want to do is to perform the case analysis, because remember the discriminate actually performs a case analysis itself. So you repeat case analysis. This is why when you use inversion many times, you have many. Okay, so first, okay, we will see the other examples. Okay, so actually we can do this case analysis only once. Okay. So the idea is to define kind of slices of this relation, relation here. And I think it's better to show that on the example. So let us go here. Probably, yes, I need to make it bigger. Okay, so this one I put it on the top. And so you can see the 3 slices, or call them also partial versions, partial predicates, partial version of next color. So here, for instance, this one is exactly like this one, but I don't have the other cases. Only one case. The case. And second difference, okay. Second difference is that this one is called next color green, because be right here you have the underscore here. So it's next color not of green, it's next color green, and as soon as green is fixed, I need to one of the first argument is fixed. So I only have a one place predicate here. Okay. So what is to be the next color green? But it's just to be orange. Only orange is the next color green. Okay. Similarly, only red is the next color orange. Okay. And so, okay. So you see, it's very easy. I just technically, I just make a copy paste of, a copy paste of this one. I put them in. Okay. First thing. Next thing. No, not finished. I need also to consider the other colors, purple, yellow, etc. So if I'm very basic, I will have how many? 4 more predicates. Here I am a little bit lazy. I take one which I call next color no for all the others, but just because I want to share the work, but it's not okay. No, nothing deep here. So for this one, you see that I have no constructor. That's the point. For all for green, orange, and red, I have respectively one constructor. For green here, I have one constructor, orange, okay? We'll see later more complicated cases where we could have several cases. Okay, at the moment I have either 1, like here, or 0, like for, say, yellow or purple. Okay, and now the next point is to define something which is, okay, intuitively equivalent to next color, but which is expressed in a functional way. Okay, so we have this definition. Now it's not an inductive; it is a definition. Okay, so it's a function. Okay, I write it this way because C is the argument of the function, and it returns a predicate, a one-place predicate. Okay, and you see that for green, I return the first slice. Okay, and for orange, the second slice, etc. Okay, you see, and for all the other, yellow, blue, etc., I return the last. But it could be more picky, but okay. You see the idea. So here, by the way, you see that here I use something we have introduced in the maybe second lecture or third, I don't remember, with the wow function. Because basically what you do is to take a value and return something which is at a higher level. It's a predicate. So remember for the wow, I think I have no, coq, yes, coq 0, 1, theory 2, yes, I think this is 1, yes. So I define wow, which, okay, the argument was here. It takes a traffic light color and it returns a set. So it's not a problem, but the idea is the same. A small difference is that here we have set, and in my other example, I have prop, or more precisely, I have a function from color to prop. But the point is that I have something which is at the level of types. Okay, so here I return the nut, etc., and I could use this function to define something else. So by the way, so this ability of Coq to define this kind of functions, which is not available in usual programming languages, is called large elimination. Okay, we take a basic value and we return a type, something which is higher. Okay, so let us come back to the previous one. So we just reuse here the ability to use large eliminations. Okay, and now what remains to do is to say that actually I don't need equivalence. I just need to show that if I have a next color, then I can get a next color dispatch. So I only need this implication here. Okay, so let us put it in the middle of the screen. Okay, so here I give the full script. It could be done I give the functional version just to show that explicitly how it works. So I take a next color, and at usage, I will assume that C1 will be known, but anyway, for the definition, I just say that, okay, so this is the destruct of NC. Okay, so the previous refine, you remember. So I perform pattern matching. I match this NC. The NC is here. Okay, I match this thing, and I say that NC could be NCG, NCO, and NCR like before. And here I have to return a next color dispatch of green and something. Okay. So see that here as NC, as I am in this case, so C1 is forced to be green, and by the way, C2 is forced to be orange. So the point, so here the type of this branch, next color dispatch of green, orange. And next color dispatch of green, orange returns this predicate. And this predicate it is okay. Sorry, yes, here. So this predicate here is defined there, and you see you have only one constructor, which is this one, but only one. I don't care at this moment. I have at least one, which is this one, and it is precisely its type is precisely what I want. The type I want here is let's call this dispatch of green, orange. Oh, sorry, it's next color green. Okay, let me repeat. Here, I need to return a next color dispatch of C1, C2. C1 in this branch is green. So next color dispatch of green C2, you compute this. So you need to make the computation at compile time. Okay, I compute it here. So with green, I read. So the type of the branch here is next color green. The type here is next color green and next color green. Okay, so in order to return it, so okay, NCG, you see that NCG prime has exactly the expected type. So maybe it's interesting to see an interactive definition of the same thing because it's maybe also we'll see really the relation with what we do in script mode. So I will in this session write it like this. So I will define it interactively here. Okay, so so I make a proof. Okay, so I want to make a match on NC. So this is destruct. Okay, so I will say destruct NC as and I have 3 cases. Okay, I can be this like this. Sorry. So 3 cases, and in each case, I see something like this. The first thing to do is to compute. So I make the computation. I can do the computation because, okay, this function is defined. It's not opaque. It's not a theorem. So I compute. So I can now compute it in each sub-goal, CBN, say. So you see that now what I have to provide is a next color green of orange. A next color green of orange, okay, it is exactly what I have here. I can say this is this constructor. Okay, so I will just say, okay, there is a constructor. Okay, there's a tactic in Coq saying try a suitable constructor. So here I have only one, so there is no chance that he choose a bad one by if I am unlucky. But in that case, it will work. So you see, the theorem can be proved in one line. Usually, I proceed in this way. Here, we can show you explicitly what it is, or we can do the script. Okay, so let us.
When you choose a command constructor, so all the constructors you have to find.
Yes, he tries. I think in the top to bottom order. And the first which could work will be chosen. It could be not the one you expect. Okay, but not restart, reset. Next color inf. So yes. Okay, so we have so this code, the code we have here is exactly the one, this one. Okay, we could print it. Okay, you see. So except that Coq is more precise. Okay, on the fact that the type which is returned in each branch is computed in this way. But okay, you see exactly the same thing. And sorry, we don't see everything. Okay. Okay, yes, yeah, we see the result, and Coq adds the type information. But, basic. So I have a more less heavy definitions here. Okay, without all the type information. Okay. So. Okay, and that's all. So you see, basically, it's a little bit of work, but each step is very easy to understand. Okay, just take the original inductive type. Then for each slice, I define a partial predicate, and then I define a dispatch function, and then I prove that given a proof of next color, I can get a proof of next color dispatch. And this one is more interesting because if C1 is known, then this one will return a predicate which is much simpler than the original one. It will return the predicate which has exactly the case this. Okay, so let us try on next color 3 using small inversions this time. So let us see. So the script is quite detailed, but after that we can make it shorter. So introductions as usual, and then okay, as usual, nothing special on NC1. So basic destruct. Okay, and now it's we start to need inversions. So let us check. So the point is that I will not write destruct of NC2, but destruct of next color inv of NC2. And that's all. I just need to add this function applied to the hypothesis, the name of the hypothesis I want to invert. So let us check the type of this thing, and that we see that the type of this thing is exactly after computation. Next color, beware of this is a predicate. It is not next color applied to orange. You have the underscore here. You have this function applied to C3. Okay, so and so as it is a next color range of C3. So okay, again we know that we are in. So this is this predicate with only one case. Okay. So and you see, by the way, that no need to have additional equalities, just works like this. Okay. So okay, so now I destruct. So instead of saying inversion of NC2, I say destruct of inversion function applied to NC2. And so I have only one case. And beware, look at the C3 here. So you will get, instead of C3, you get red. You have seen? The C3 has been replaced by red, and no additional equality. Okay? And so now so that's the same. We have a red here. So I will destruct next color inv of NC3. Okay, and so this one will choose the right specific predicate, the right slice. Okay. Okay, and reflexivity. Okay, and the other goal will be handled in the same way. So let us. Sorry, I'm not in the right place. So with only one line of one command here, I say that I make a destruct on NC1 followed by an inversion of NC2 written in this way, followed by etc. Okay, and reflectivity at the end. So at once, it's finished. Okay.
But I didn't quite understand. So why in this case is simpler? Using what you have used.
I used
Next color.
yes, everything is here.
Go by the definition, but it's not in the.
It is here.
Yeah, this one.
So the point is that, so you don't care. Mm-hmm. So the important thing is that when you call this function, the important is that you apply it to, okay, so by the way, yes, I use these curly braces to say that C1 and C2 are implicit arguments. I only write the NC color, the next color argument, okay?
So in theory, you only apply it for one argument, right?
That's right.
Yeah, you partially apply.
Yes, so I need, yeah, that's right. I need an inversion version for when the first argument is specified. If it is the other, I need to redefine the same. Okay, okay. You have a. So when I apply this to, okay, so let us see here. Okay. So I apply my function to NC2. So actually, it's the full thing is next color apply to orange C3 NC2. If I write all the arguments, okay. So, but the point is that I apply this. Sorry, I apply to this argument which has this type. Okay. Okay. So I apply to NC2. Okay, so maybe what I could do is to have the other. Okay. Yeah. Okay. The point is to have. Okay. The code is not important. What is important is the type here.
Yeah.
Okay. 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 So what you have to say is that when this function is applied to NC2, so to this NC2 of type next color orange C3, so I know that actually so okay, the only point is that okay, I will return an this is the only point. Don't care about the code. The only point that you will get a next color dispatch of C1 C2. That is, you will get a next color dispatch of orange and C3 in that case. Okay. The result of this one is next. By the way, this is what is written here. Next color orange of C3. That's the point. And this one is much smaller than next color applied to orange, applied to C3.
Because you have only one constructor.
Because I have only the relevant constructor. Yes, that's the point. So only one case to consider. And you guess if you have a huge inductive type with many cases, like in the concept context. Okay, so you get only the one. Okay. So by the way, historically, a variant of this technique was invented more than 10 years ago when I worked with Xiaomu in this room. So we use a variant of this technique, not with. So the difference is that instead of having, so the important point was to have at the end something like this. Okay, the difference was that this one was not defined using slices. The slices were not defined with predicates, but they were defined with some kind of continuation-based translation of this one. Okay, so it was a definition instead of an inductive, but So the mechanic was a little bit more complicated to explain, but it worked. It worked perfectly well as well. Okay. So, but using predicates, I think, is much more intuitive. Okay. So okay, so we have this one now. Okay, so if you understand this, you understand almost everything. I have to consider a bigger predicate to show what happens. So let us see again for purple what happens. So nothing follows purple. So I have okay. So I have a color C2. Well, why not? Could be, and then some condition on C2 saying that it is the next color of purple. So basically there is nothing like this, and I can send in that case I can prove anything. Okay, so again I apply my function to this hypothesis and see, and I get a next color no of C2. Because okay, a next color no of C2 is a predicate without constructor, so I have 0 case to consider. Okay, so if I perform the destruct, it's something with so okay, let us sorry. Yes, so it was not synchronized, so you see that it's finished, no more goals. Okay, and yet it's interesting to see the code explicitly. So I do a refine match next color in of NC with a 0 case and just a usual match with. Okay. So let us continue with an example which is a little bit more impressive than just predicate with 3 cases and nothing behind them. So it is an artificial example without special interest, but just to show to illustrate the technique. So that I can explain with this drawing here. Okay, let us put it at the top here. Okay, so I have a predicate. So it is so the idea is that blue is followed. Okay, I said what's the bottom. So as before, green is followed by orange, which is followed by red, which is followed by green. So okay, a similar predicate, and blue is followed by indigo. Indigo is followed by purple, and purple has nobody, has no followers. But indigo has also another follower. So it's followed by D, such that yellow is followed by C for some C, and C is followed by D. So this double arrow means the previous next color. So I will change the name. I will call it yet another next color. Okay. And it will use the previous next color. Just to show, on this example, I want to show 2 things. One, which is I could have several constructors for a given pilot for indigo. Yes, you have indigo purple here. Okay. Another possibility to have indigo of C, such that I have yet another color of yellow returns the C, and the previous next color, so I can use other predicates, CD. Okay. And you see that okay, this predicate is recursive in some sense because I reuse yet another color in this branch. So you see this example looks more okay. It shows more features of what can be written with inductive types. So yellow is followed by yellow. Why not? Okay. So okay. So you see. Okay. So basically, I have something which looks like before, except for this indigo, which is more interesting. Okay, indigo is recursive, etc. Okay, but so I say that because you have to take some care on how do you write the slices, the partial predicates. Okay, so let us put it on the top. So, yes, before writing the small inversions, maybe I don't need the previous one. Okay, I need to recover my Windows. This one. Okay. Okay. So let us first see that I can prove again that repeating 3 times yet another color, I always get the same as before. So you can see that on the here intuitively, because okay, for green that's the same, green and red. So these 3 are dealt with as before. Yellow 3 times, yes, yellow. And for if you start with blue, for instance, 1, 2, I have nothing, so it's irrelevant case. And now, if you look at what means this branch, if you think more, you see that it is a dead branch. Why? Because D is obtained by first looking at a follower of yellow, and it is only yellow, okay, and then I should find the next color of yellow, but the next color in the sense of the previous predicate. So the previous predicate was only defined for green, orange, and red. So basically here I have no possibility as well. So basically, actually, these 3 colors here have if you compute their next color, their yet another next color, after 1, 2, or 3 times, you have nothing. Okay. So okay, so let us check using the powerful inversion technique of Koch. So we state, oh sorry, okay, I would like to have this one on the top, or maybe not. This one, okay. Let us move on. So we introduce, and as usual, so case analysis, basic analysis on the first, and then inversion on the followers. But I have to be more careful because I cannot do that within one line. So first one, so I have 7 cases to consider. I don't know how many. Yes, 1, 2, 3, 4, 5, 6, 7. Yes, 7 cases. Okay. All of them are very simple, except the one to it's the third one here. So the third one has 2 colors C and D here, and then a condition on C. So I will call it like this, and a condition on C and D. I call it NC because this one is the next color. This one is yet another next color. Okay, yet another. Okay, so let us do that. So first case. So I have an indigo here. Okay, so I need to exploit this hypothesis. So I will just invert it, okay, and substitute because the Koch put equalities. Okay, so I get that that I have a purple instead of C3. Now, sorry, I have, yes, C3 is purple, indigo, I don't know. C3 is purple, yes. And okay, but Koch changed also the order of hypothesis. Okay, so I have this, and then so I got this purple, and now I can invert this one, and yet another color of purple. Okay, sorry. For this one, I have 2 cases, because if I have an indigo, it could be this clause, the first one, or the second one. Okay, so inversion actually provides these 2 cases. So be careful. Here I have one goal, after inversion, I have two goals. First goal for this one, so this one, so I have purple, and if I have purple, actually, yes, I thought, yes, purple, in this definition, there is no colors following purple. Using yet another color, okay? You see, you never see a purple here in the first position, okay? Here, 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 okay? So if you look at the possible cases for this one, there is no cases. So, sorry, here. Okay, so indigo, so let us invert it, and it's finished. Next one, so this is a complicated one here. Okay, so this one provides us, so you see that Koch introduced a hypothesis for the inversion. This here, it is inversion. So we get a hypothesis for this one. Yes, this is this one, but C is a C3, and another. So and you have some yes or something. So the point here is that Koch invents some names. So D is the name D here comes from my definition, but for the other conditions here, we have some names invented by Koch. So Koch tends to use H like hypothesis, and then when after 100 steps you have H 117, H 201, and so on. Okay, you have a number of names invented by Koch. But anyway, you can move on. So in this case, for instance, you can say, okay, I will invert this one, and there is only one possibility for C3, which is to be yellow, according to the, if you look at the possibilities, you have only this one. So let us invert H. So you get the yellow here, and then now you have next color of yellow, so this next color here. It says that, okay, C, now I found it, it is a yellow. C is yellow, and D should be the color, which the next color of yellow according to next color, the previous one. And there is no one, remember? So inversion will say, okay, okay, finished. Okay, and so on. So, okay, no need to, okay, it's always the same kind of reasoning. So here, for instance, we have a purple. So, nobody here. So, okay, that's finished, etc., etc. Okay. So you invert, you repeatedly invert, you revert, etc. These three lines, okay, and it works. So you are happy. Koch is able to do, and you can, if you are brave, you can print the contents of this theorem. So you have a script which is a little bit boring, but not that long, 10 lines, okay? Okay, and if you print it, it's not boring at all. You have all this. Koch works, huh? So you can see more, how many lines? 860. Okay, okay. So maybe yesterday I made my try. Okay. Maybe it depends on the way things are displayed. Okay, but basically something like okay, okay. Or we will say something like this. Okay. Okay. Now let us try small inversions. We will then understand what they are called small inversions. Okay. So same technique as before, but be careful. So okay, I will repeat the original predicate here. So you see what we have. So for I consider all the colors, all the pilot one by one. So it could be blue, etc. Okay, so when it is blue, okay, only one possibility, this one. So like before, nothing new. Indigo is an interesting one because for indigo, I have two cases. So the first one is when the second argument is purple. Okay, so I have a first version, which is like this one. Okay, it is a copy paste of this one in some sense, except that I return, okay, instead I have an underscore here instead of a space. Okay, sorry, here. And for the second one, so again, you can see that I have a copy paste. Be careful. For instance, here I define yet another color indigo. And what I use here is yet another next color. I don't try to make anything clever here to try to recover some kind of recursion. I don't care about recursion here. This is the important point. These two lines mean that, in some sense, the predicate here, the relation yet another color, is recursive. But an important point is that inversion has nothing to do with recursivity. It has only to do with case analysis. We only look at one step. Okay. So basically, I just copy what is on the left of the arrow here. And okay, so on the left, I have for all CD, blah, blah, blah. So all this part, actually, okay? All this the blue part is copied here, passed here, okay? And then the conclusion is just the adaptation. I adapt the conclusion because here I have one place predicate. That's all. Okay. So this is okay. The only thing you have to be careful. So just copy and take care of the arguments. How? So okay, the first one doesn't exist. It's just the name of the predicate. Okay. And the rest is as before, nothing new. Okay. Then the dispatch function is exactly the same. So you don't have to think here. You just write. Okay, I consider all my colors. So in this case, okay. So I have okay. I don't need. I have no. There is no point to share anything. I have yet another color for purple, a specific one, which is used here. And okay, so. Okay, you see it's basically the same idea. And for the inversion lemma, okay, in this case, I was lazy. I just proceed in script mode. Okay. So destruct, I use E constructor because for this one, there is some witness to be guessed here. No, sorry, D. D is not present here, but using E constructor and E assumption. Okay, so you can, of course, print it. Yes, there is nothing special. Oh, yes. Let's just print it just to see. Print. Okay, you see that it is basically like before. So coq is precise on the type, but so you see each time for each constructor, I have the small version of the constructors. I mean the and for this one looks complicated, but it is only because coq write explicitly all the types. But okay, let us see here. Okay, so I will try to write it to here again. Okay, we could leave it, but okay. Let us try to an H. Okay, some next color. Okay, that's the name, but I don't care. Okay, so you see, oh, you even see fun, blah, 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 applied to CDXY, but and CDXY are even this one. So you can even perform a regex here. You could see that actually. You could just write this if you are explicit. So instead of C, you write a C, here a D, here X. Well, the name is a little bit strange, but okay. Okay, at the end, this is what you have. If you write it explicitly, it is this one. So you just see that, okay, if I have this constructor, I return the corresponding version, which is here. Sorry. Okay. It is below. Yes, this one. Okay. So I just apply to CD, etc. Like before. So you see okay. So I'm lazy at writing it, but explicitly not that difficult. Okay. So now let us prove it again using our trick. Okay, so inversion. Okay, so okay, not sure that I need. Okay, I will keep this one here. Okay, so introduce. So same as before, destruct. So this is no change. Like nothing new here. Now I will use, instead of Coq inversion, my inversion functions here, and you see that this one returns okay, this type as usual. Okay. So here you get two cases as before, but no equality, nothing. So look here. By the way, it's even simpler to follow because I have no Coq with inversion tends to change the order. Here, the order is respected. Okay, so you will see that C3 will be replaced by something here and there. Okay, let us destruct. Up, I have my purple, and I have two cases. Okay, as before, so it's normal. Okay, so first one. So I have yet another color of indigo purple, and okay, so this one, okay, actually it is the previous one. It is already used, but now I want to use this one. I claim here that I have something which follows purple, which actually there is nothing. So the destruct of this one will just say, okay, zero case. Okay, and so now for the next interesting one with yellow. So yellow here. Okay, this one I will here I will get that C3 will become yellow everywhere. By the way, so all the C3 in the goal will become yellow. Up. Then I have this next color of yellow, which is absurd in some sense. Okay, does not exist, no case for this one. Okay, so etc. So basically the same idea as before, like for inversion, but just using a basic destruct with a basic function. Okay, okay, so let us okay, so nothing new, just the same mechanism. Okay, we can even write it in a small, try to share something. Okay, so technically nothing new here, nothing deep here. Just saying that, oh yes, I destruct, and then but I could do that also with inversion. Sure, because inversions tend to put names you have no control, so or maybe in that case it was because it's simple, but okay. Okay, anyway, here there is no problem. I try to destruct the first, the second, and use reflexivity. This is because, yes, basically I say that each time the C2 will be forced here, use here, C3 is forced, C4 is forced, then at the end I expect to get something like C4 is equal to C4, okay? So this is the basic case, basic situations like before, and I'm left with two more complicated cases corresponding to okay, the clause corresponding to this part of the, sorry, here. When we are in this branch, okay, we need to think a little bit more. So here, okay, so then I just reuse the script as before. Inversion of this one, two cases, inversion, second cases, first inversion, followed, okay, sorry, this one says that C3 will be yellow, and then I will be in a dead branch. Okay, let us print it. So still some work, but not that long. It's small. How many? I have 87. So okay, I would say about. I don't know. Okay, depends on the display from the room on my screen or whatever. So basically 10 times less as big. So it's better for the planet. Okay. So okay, so I finished this part. So I will just so the take-home lesson is that you have pros and cons for this thing. So the inversion, the basic inversion of Koch is you have nothing to do. Just use it, and it's convenient. Okay, okay. It's so. It reduces. Okay, the drawback is that you have hypotheses and you have no control on their names. So when you repeatedly use inversion, so the kind of thing that Xiaomu had to do in her PhD thesis, because she worked on the semantics of consortia with big, we say huge inductive types with many cases and many. So a full control was mandatory. So okay, that's why we try to have better techniques similar to this one. And okay, and also you have these parasitic equalities which look a little bit strange, because basically you see that there is no need for equality. It is just because some kind of artifact similar to this famous souvenir trick. Okay. So for small inversions, there's just a converse. So you have no black magic. You see everything very clearly. You have to work, okay, and you have small proof terms. Okay, and also so another thing is that small inversions use this large elimination trick, which shares actually many. If you don't use it, you have to redo this case analysis, this second level case analysis many times. Okay, so it cannot be shared. Okay, so now we just can use that for natural semantics.
Yes,
we could, yes, we can make a break, I think. No?
yeah.
Can, so the technique is not really published. So actually, the technique, the continuation type technique version was published with Xiaomu in 13, I think, at ITP. But then I have publication or something. I have a paper at Types 2 years ago. Okay. But it is very short, and you cannot understand, I think. But the published material actually is in my teaching scripts in French and now in English. Thank you. Yeah.
Is it possible to alter this?
So we think, but especially because we have last September for, and yes, we progress quite well. So we already able to produce automatically the slides, the partial but slash and actually the input was internal in the tool as well. So with some restrictions, because if you consider the new case, okay, you have more complication because some arguments become, so you know, the difference between indices and parameters. So when you have something before the column, the parameter. And one thing we can do with this whole version is convert the number of indices into parameters, which makes the test report convenient. But this is checked when there is a lot of complication because when you do things automatically, you have to deal with the brain indices. So he doesn't use metacode, but yes, after 15 years, it's time to start. Yes, especially if you want to use technique, so very need to have kind command, I think, the style of scheme, you say, you speak information. So please give me the verification for this information. Next week, I will show you another way of making version that I think that we are doing much more information. They call projection. Because inversion I think so this technique is more powerful than the inversion approach. Well, the good communicated you the different types and fine. The thing we had the technical work and the system one is
通电的对吧？你是什么电脑？因为我已经在那个，我自己上家的，正常那个，还有你也是中国人用，都没明白。你这放电话，啊，你听得懂？你在用电脑啊？应该可以，是这样。好像是这个啊，这可能是那个。好像是领导，人现在蛮少的，应该看那个让一起。 我忘了那个，你看一下。
啊，
Ah, je crois que c'est... Ah, I understood why the number of lines changed. Because I made the font bigger here, and if I use a very big font, I have found a small number of lines, only 15, but this is because Coq does not display everything. Yes, okay, I try to see to save some places, but yes, here, for instance. How to go on the right? Ah. So, but basically, when Cook has not enough room, he puts some edits. So that's the reason. So basically, yesterday evening when I made the try, I really got more than 900, but I had the smallest fonts, so I had everything. But I hope so. I did not check everywhere. Maybe it's actually still more. I don't know how to. Ah, yes, this way maybe. It's difficult to see what happens. Ah, maybe like this. Bon, we should have some. Ah, here. Okay, here you can see here. You see? Here you have this. So there are so Coq is cheating at displaying at this place. Okay. So I will say I'm sure it is reasonable. Well, probably you say with the option of Coq to for displaying.
Yes, so displaying without.
Yeah, can you export it to a file?
Or probably yes. Another way to compare also is to save what you get after compilation and compare the
Yeah.
PO file kind of
Yeah,
thing.
yeah,
So
yeah.
you basically you see similar figures. Anyway, you never want to read this code. So well, I'm not sure that similar to it, but in principle, as you can define as how to say, as any definition which any object which has been defined with with code with a script, at the end it is a function. Okay, so you could say today I have a function with a somewhat complicated dependent type, for instance. So I want to develop it in an interactive way. You show that that's possible. And from time to time, it's convenient to use inversion. But at the end, what you really think this thing as a function that you want to apply and to compute with, and maybe even to prove things on this function. So if you have a function defined this way, to make proof on this code, you are dead. Okay. That's impossible.
Yeah.
While with small inversion, it was still a little bit big, but not that big. So you still have a hope. Here you have no hope to use such definitions to prove anything, or unless maybe you use some kind of abstractions, abstracting the part where you do the inversion. Okay, maybe by thinking more, maybe you can, but the situation is not very good at the beginning. Okay, so let us restart. So I wanted to finish by some questions and remarks in the classroom at the end. So how to say, yes. So one thing I forgot to mention is that in some specific situation, situation with dependent types, usually you don't meet these situations unless you are doing some somewhat complicated work, but it could happen. Sometimes people try to have some dependent types in some corners, and so you have to know that sometimes the standard inversion fails. This small inversion work in such situations. Okay, in practice, not so often, of course. Otherwise, people would have asked the Coq team to have a better inversion. And another question was, what about automation? Yes, because you could see that technique basically you use the same mechanism. So it's not that difficult to write things by hand. So why not to try to automate it? But actually that's what's work in progress. So I have a PhD student and a colleague who work on this part. Okay, so hopefully, it's seems to be in good shape now. We are already able to produce the auxiliary definitions in a number of typical cases. No, we have to make this still more general, but we have good hopes to have something usable automatically. Maybe after 1 year or 2 years. Okay, so let us go back to the natural semantics where we were yesterday. Just need to, oh yes, so I need to this one, this, no, here. Okay, so we went to a point where we started to talk about inversion. So, because it is interesting to see an application of this technique in a real situation, more real situation. Okay, okay. So this was. Okay, no, I have to go this place, yes, because the application comes later. Okay, so we have another shorter explanation of inversion, of small inversion here. But okay, so now it should be easy for you to follow it. Huh? So here actually, so how to say that? Okay, so maybe I should first cut my window and I want to. No, I don't have. Okay, I think just do to NS. Yes, this place here. Okay, so basically we have our. So this is the equivalent of next color. Okay, so your relation this time with the 3 arguments. And okay, number of cases, and you see that typically the way we use this relation is to reason on okay, some hypothesis, something which says that we have a big step between a state, starting from some given state and knowing for using a specific instruction. The point is that the instruction here is quite common. From time to time, the instruction here is specific. So instead of, okay, as usual, you would like to use the inversion, an inversion mechanism to say, okay, only for instance, this case is interesting, or only this one. So in the example we'll see below, the one which will be interesting will be something where you have an NSSEC. So actually, the way I proceeded here was to say, okay, let us just consider this slice of NS. Okay, so exactly as usual, I have the same conclusion. Okay, which is similar to this one. So except this time that, okay, you see that if I know that I am in a sec, okay, so this sec has 2 parameters, which are I1 and I2. Okay, so my predicate will have 2 parameters instead of one, just one. The sec has already been decomposed at the dispatch step. And for the rest, it is exactly the same. I have a copy paste of this at this place. Okay, so actually, okay, so I1, I2, SS2 were given from the beginning. So okay, so they are put in the parameters, but basically, they are still there. They were in the fall. Here they are in the parameter, but they are there, and only the S1. Because you see that the S1 is not present in the conclusion. So the S1 is a witness to, which says, okay, I have to find some intermediate state between S and S2. Okay, so this rule says that, okay, if I have some S1 such that exactly the same as here, then I have this slice of NS. Okay, between S and S2. Okay. And here I just say, okay, I am interested in this predicate for some reason, we will see later. And I want to prove, so this is the equivalent of the before. So I call it inversion of sec prime, something like this. That's the name I choose, which says that if basically if I have a NS from this specific instruction, depending on I1 and I2, and state initial state S, final state S2, then I should have this predicate between S and S2 and okay, I1 and I2. So this predicate, this one, okay, with only one case. Okay, so in some sense, I prepare the work of that I want to do, and actually this predicate, I can prove it using the standard inversion of Koch. Okay, I can do it otherwise with a small inversion, but I can use also the inversion. Just okay, so I prepare my work with the standard inversion. Okay, so what I say is so let us specify. Let us. Okay. So here. Intros. Okay, so we have our hypothesis, and so here I say okay, instead of doing my work by hand, I will just use Koch inversion to say okay, please help me to see what happened in this case, and the Koch will be happy to do that for me. Inversion. So of course with a lot of equalities, okay, and strange names, okay, like this, but okay. So, I don't care. This is in a small lemma. So later I will now see this. So okay, let us clean that, and okay, and I see that I have exactly the material I need to prove that. Basically, I need this and that. So this is here, and that is there. Okay, okay. So you see, okay, basically very easy. Okay. And sorry, I want to put this at the top of my screen. Okay, so just to say that, okay, you instead of using inversion, you can do things by hand. And actually, okay, this way, okay, so okay, let us follow the script. So actually, so in this case, I will here I will define a kind of specialized version of the previous the first part of the lecture, because I am only interested in one case, the case of the sec. So all the other cases, I will not make a specific work for them. I think that this is closer to the work we use at the time of the PhD of Xiaomu. So okay, so I have all the other cases. So okay, I don't need to say anything here, and I say that if I have no, sorry, I define my dispatch as follows. I say that if the instruction is a sec, in this case, I am happy to answer with this constructor, which is okay, the specialized one, okay, and for all other, okay, I put something which is enough. And now my inversion lemma says that if I have, so the same statement as before. Before we proved it using Koch inversion. Now we use it just with a very simple pattern matching. Okay, you see that this is much smaller than the Koch inversion. Okay, so let us see the details. I say that if NS is a NS-sec, okay, then okay, I return exactly the same thing with S1. So the S1 I got here and the two components, the auxiliary conditions for the sequence. And in all other cases, I return the trivial predicate defined here. Okay, so this is enough for what I want to do. So it is a kind of simplified or ad hoc appropriate version of inversion for just sequences. Okay, and okay, another, what is it? Okay, no, sorry. No, this is. Ah, okay, no, okay. So this is a kind of spatial inversion, and use it for the lemma I wanted earlier. Okay, but basically that's the same. I think we could just okay. So we see that here we just apply the previous thing. Okay, don't know why I using two steps instead of just once. I think okay. Nothing deep at this stage. So now let us see how we can use this new power. So I defined another there is another way of defining the semantics of the Wayne language. So this one is very similar to the previous one, except at one place. So if you see here, actually that's the same everywhere, skip, blah, blah, blah. And the only place where we have something new is for the last one. So here the last one is defined in a pure way. I just explain the semantics of while. Sorry, here I explain the semantics of the while instructions in terms of the semantics of I, and also, of course, I need the semantics of while itself. But okay, and here it's a little bit different. I explain the semantics of while using the semantics of the sec. Okay, this is something which is okay. You can find papers using this kind of thing. So you define the semantics of previous constructs, and then the next construct will use the semantics you defined before. You see that you have the sequence. You see that, okay, in this case, it is as if my program was written as I followed by again the full loop. Okay, and okay, so you have these two versions. Either I have this followed by that, or I have to. Okay, I say that I use what has been defined before as this. Okay, so intuitively, okay, it should be equivalent, and it is equivalent, and it is interesting to see if it is easy or not to prove the equivalence. So there are two directions for the equivalence. The first is so if you have an S, then you have an NS prime. So this one is completely nothing new. So basically, you introduce your hypothesis and you will reason by induction on the NS, because so you see that you will get induction hypothesis, for instance, in this case, etc. You have a induction hypothesis, and you just apply the induction hypothesis. So you can do it really. There is no difficulty. So sorry. So all the goals are considered at level 1 for my students. So okay. Except the last one, maybe. Okay, where we have okay, maybe okay, so okay, you have to think a little bit more, but basically the script is very simple. Oh, as it is a little bit long to type. I will not waste my time here to type it. What I can do maybe is to show the solution here. Listen. Oh, I hope I have it. Oh, yes, it is before. Oh, yeah, because there are some other exercise after. This one. Okay, I make it bigger for you. Okay, so you can see that oh, some French has been left. So basically, you see that the level 1 questions are very just applying some the obvious constructor. And here you see that we use, for instance, the induction hypothesis for the sequence. For true, okay, for if, sorry, okay, sorry. Okay. Okay, for the if true, you apply the induction hypothesis as well. So nothing deep. And similarly for the if false. The while is simple as well. And at the end, why level do I don't know? No, I don't see any difficulty. Ah, yes, because, okay. In this case, you have to, well, maybe we could try to see what happens. Not that long. Okay, let us go to this place. Just to see what we have. So let us go to the next goal. Okay, so here we have okay, the name, okay, induction hypothesis. I should rename them a little bit. Okay, so I have an induction hypothesis saying that, okay, I can go from S0 to S1 using Sn prime as well, and I go, okay, from S1 to S prime to the using this induction hypothesis. Now, I want to prove that I am able to go from S0 to S prime using the new semantics. And here, the only choice is to use the okay, this rule, which says that okay, so I have the precondition true here, but I need to use this thing. So I will, if I use my constructor, I will have to produce a proof of this one, but it's not difficult. Not difficult. We will see that it's not difficult. So I apply the relevant constructor here. Okay, and then okay, I have this condition, but I have it. I had it from the very beginning. Okay, and here it is interesting. Here I have to prove this, and here it is not directly the induction hypothesis, but what is that I see that I have to prove this for this sequence. Okay, then I just use the constructor for the new constructor, the constructor for the new semantics, which is Sn prime sec. And so here I will just use the induction hypothesis. I use the E apply because I have the intermediate state. Otherwise, I could say Sn prime with S1. I can say explicitly as well. Okay, so anyway, I'm lazy. Okay, please find a proof of this one. Yes, here's a proof. This is just the induction hypothesis. Okay, and then for the last one, S1 has been instantiated. So for this goal, I just reuse this time my induction hypothesis. So you see, basically no difficulty, just okay, you are just driven by the goal. You see that according to what you have here. Okay, what you do? Okay, so nothing difficult here. Now, okay, let me put this here. Now for the second one. So this is the easy direction. And for the other one, it's quite similar, except at the end. So you see, again, the goals for the first, it was the same because you see the definition is the same, except you have NS prime instead of NS, but the rest is the same. So, okay, so just a basic translation, very routine. So. Okay, So here I chose to leave the exercise. Now, what is this goal? Okay, so here it corresponds to the last goal, so the interesting one. Okay, so now I have two induction hypotheses talking about. No, this is original, but the induction. I have only one induction hypothesis this time. Okay, because of the definition. Sorry. Because of the definition, remember that I try to put it into. Okay. So the interesting part is here for ns, and for ns prime. No. So here, okay, we have everything here. So okay, so remember that for ns prime, we had this eval, which is there, but for the second, the interesting part is here. We have only one condition, so I have one induction hypothesis on this argument here. Okay. So here you cannot, because you cannot go further directly, because in order to prove this one, so which is here, I need to, so this one is easy, but I need to have two results. One saying that, for I can go from S to some S1, and so on, and I don't have this directly. Here I have something which is just says that, I can go from S to S prime. I don't even have some S1 to talk about. So what happens here? So I guess I try to destruct, but so you see that destruct this one will not work, because destruct will forget that we have a sec. So the destruct just makes many stupid things. You don't want to see them. So basically you see that you should recognize here that it's not the right thing to do. So let us go back here. The point is that you have to recognize that here you have a specific usage of NS. So it is time to use inversion, because it is NF of a sec, blah, 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 etc. It is not an NS with something with a variable here. So here I will use my lemma, which could be proved in some way. And we see that my lemma here says that the applying if sec on hypothesis returns a proof of this predicate, which is much more simple. This is a predicate with only one case, you remember. So if I destruct it, now I get the two hypotheses I need to finish my proof of NSY2. So sorry, here. The two hypotheses I need to apply NSY2. So now I can say apply while truth, and now it's finished. First condition, evaluation of the condition. It's available here. Next one. So, and then I need to go from S to some other state unknown, but we have it. You see that just using. Sorry, I should be here. Yes, okay, and then second. So you see that the point is that at this point, I go back to this stage. The point is that I need to decompose this induction hypothesis into two pieces, which respectively will give me the necessary material to finish. Sorry. Okay. I put my my cursor in the here. No. Okay. So so I need to decompose this hypothesis into two pieces, which are the right one for here and there. Okay, so inversion is the right thing to do in this situation. So now you can choose your style of inversion, but anyway, so here I have a kind of mixture between Koch inversion and small inversion, but okay, that's all. So you can see, so this is a typical situation. Okay, I mean, I go back here. It is here, typical situation when you make reasoning on semantics of programs. So you have hypotheses because you reason either on a specific program or a program which has some shape constrained in some way in some other. So you have some hypothesis on the semantics of something which is a little bit specific. Okay, and then inversion is the right technique. Okay, and if you are brave, you can try another version of the while language. So I just mentioned the exercise now, but I will not solve it. Just to show you what is feasible quite easily with okay, just training of the previous material. So okay, the repeated language. Okay, let me go here. So the repeat language is like before, except that instead of the repeat instruction, the while, I have a repeat, which intuitively says, okay, but repeat the body until some expression corresponding to this AST is evaluated to true. Okay, and the semantics, okay, so, okay, as usual, you have to think how to, okay, it's part of the exercise to design the semantics. Of course, be careful. Okay, there is even some examples here to check that you didn't write something wrong here, because of course, if you write the wrong semantics, okay, maybe you could prove some things very easily, but it is not what you expect. So some examples are always good to check that you get the expected result. So this is like doing tests in programming, usual programming step. Okay, then now what is interesting is to say I can translate a repeat program into a while program and conversely. Okay, and you have to think a little bit. Okay, so this is not the solution. It is a fake solution. So you translate the repeat skip into the skip and so on. Okay. So translating the while into repeat, I think is easier direction, because a repeat to a while, because when you have a repeat, okay, but it's just a sequence of the body followed by a while. Simple, and don't remember if inversions are needed or possible. And the other direction, I think, is yes, is a little bit more complicated, because if you have a while, how to compile to make a while loop only with a repeat. So you have to make a test before entering the loop. Okay, so you make a if, and then if the if is has a good value, you skip. Otherwise, you start to repeat. Okay, just nothing complicated, but be careful. And okay, and you can prove everything. So I have the solution here, just correction. If you have a here, just to look what it looks like. Okay, just to see if it's long, but okay, so okay, so a good training, you see. The script is feasible, but okay, you have to. And the next one, okay, just as long, but the point is to have the right definition before. Okay, you can see, okay. And then, yes, another exercise which was not in the, was the following, to show that is a typical case, okay. Showing that okay, sorry, it's French, this one. Showing that the natural semantics of Y, of the language, is deterministic. Okay, and for this one, you need all the inversions, because showing that a relation is deterministic is okay. So basically, it's something like if I okay consider an arbitrary an abstract relation R between two arguments. You want to show that R is deterministic. It means that for all x, y1 and y2, if you have the relation between x and y1, and if you have the relation between x and y2, then y is equal to y2, y1, okay? So you see that you have two hypotheses of type R something. The first one we will deal with recursive way, with an induction, but for the second one, you need an inversion because the first one enforce the shape of the of x, sorry. X, so in our case here, the shape, it is the shape of the instruction we should be forced. So here you need okay to do some work to have all the inversion. Blah, blah, blah. Okay, so according to the script, I think as I define the general SN if. Let's see. No, sorry. Yes. Yeah, here I think I have the full. Ah no. Ah, maybe not. Bon. Okay, well, no, I think, no, I have everything. No, okay, here I had, yes, I did all the work here. I have, see, you have all the slices, all the partial predicates, and then the general dispatch. Okay, so no cheating. So, okay, a little bit of work, but okay, it's not difficult to type. You just need, okay, depending on your speed, but okay, between 2 and 10 minutes, I don't know, something like this. Okay, but because it is still it is a small semantics. If you take the semantics of a C language, it's bigger. Okay, well, okay. Here you really okay. So okay, so that's all for the. That's all for. Oh, okay. We'll save this one. That's all for natural semantics. So we have still a little bit of time. So we can now talk about the other kind of operational semantics, which is called small step operational semantics. Okay, so we'll see another another style of another style. So let's see what is this one. It is a correction, maybe? No. Yes, so I put it here. Okay, so we'll see. So it's called structural operational semantics. You are day 8 today. Okay, okay. So depending on time, I will talk about this and maybe a little bit also on certified compilation. Okay, these two things can be considered. Okay, let's start with this one. With bigger font. Okay, so the language is always the same. Expressions, arithmetic, Boolean, always the same while language. Okay, the states as usual. Get an update. So nothing new for the basic definition. Evaluation, so the functional semantics of expressions. Yes, I will. Okay, so I will. Okay, why another semantics? So you can see that the big steps operational semantics we have seen is some kind of mimics, in some sense, the denotational semantics you would like to have. Okay, we consider initial state, last state, if it exists. Now, if you the semantics hardly says anything interesting if you consider programs which don't terminate, for instance, because there is no final state to talk about. But still, you could consider programs which compute and have some things. So I will show you some example. An example of a program. It is always so. This is still based on the square program. So I considered. Okay, this is exactly the same example as before. So p square 2, p square n, exactly the same code. Okay, while not blah blah blah. Okay, so here it is the same. This program will terminate within n rounds of the loop. Okay, but now consider this one, which says exactly the same while some condition. Okay, execute the body, except that the condition is while true. So you know that this program will run forever. Still, you can say interesting thing on this program. For instance, you can say that at each time you enter the loop, you have an invariant which is satisfied. So with natural semantics, we are not even able to say anything about that. So we will see that with a more fine-grained semantics, we are able to say that we consider some invariants which holds at given places of the code, even if this code at the end does not terminate. This is one of the possible applications of small space operation semantics. Another one is that, for instance, if you consider other instructions, so here it's not the case here, but it could be considered. So let us see the language here. I could add, for instance, an abort statement. We say that, okay, when I meet this statement, just stop. Do nothing. I have no. The basic meaning is that anything could happen. Explosion. Okay, and okay, so you can have program with abort in some place. Or why put this abort? But maybe, for instance, because, for instance, you would like to avoid to do complicated computations that are not expected, for instance. Okay, so you start to make some computation at some time. So this is your program. You write a program, and you are unsure about if this program is the one you want. You are still not not advanced enough to make proofs in advance. You just want to make some tests. Okay, so you run the program, and at some point you say, okay, at this point I want, for example, to check that some predicates hold. So you compute a Boolean expression, and if the Boolean expression returns true, okay, go on. This is the assert mechanism of T. But if the condition does not hold, returns false. In that case, you don't want to continue the computation. You abort. So, okay, so this is an interesting mechanism. So in languages like OCaml, you have the exception mechanism, which performs something similar. Okay, so exception, abort. Another kind of thing you would like, which could be interesting, use a parallel construct, saying that, okay, I run some code, and at this stage, I have two threads which run in parallel, making maybe assignments on the same plate, on the same variable. Okay, okay. So you could have besides the sec, you could have something similar, so with the same signature, but with another semantic, which is to say, okay, choose, perform these two, not in sequence, but in parallel. So the big step is not good for this kind of thing, because you would like to see intermediate states where these two the two threads, okay, reach some state together. But with the big steps, you can only say, okay, I can do the first thread at once, and the second at once, but it's impossible to express that the fact that we could have interleaving. Okay, interleaving is beyond the scope of big step. What else? You could have also non-deterministic things. So actually the parallel is a specific case, is one of the cases where we could have several behaviors. Actually, the threads could run at different speeds, so you have a kind of non-determinism here. But even with the assignment, you could say, okay, I could choose, not here, this is a variable, but here I could choose between two expressions, and one of them will be assigned to the cell. Okay, again, so okay, so there are many situations where big step operations, big steps are not fine-grained enough. And typically, okay, so if you go out the wild language and consider process algebras or okay, this kind of thing, so typically you all the time you want to consider things in parallel, and so the semantics usually are given in terms of small steps. So what is a small step? Okay, it can be also defined using, it is also an inductive relation. Okay, maybe I should, what happened? Yes. Okay, so we'll see that later. Okay, so here is the definition. Let us take time to see. Okay, by the way, okay, usually it's written using, in the papers, you see rules, but okay, the rules can be expressed using an inductive predicate. So the first thing okay, there are several ways to formalize it. So here I formalize using a notion of configuration. So what is a configuration? I have two kinds of configurations. Either it is an intermediate configuration saying that, okay, I have something to run. I have an instruction. So the computation is not finished. Here is the AST to be computed, to be used for the next computation. And here is a current state. Okay, so two things, a program and a state. Second configuration, only a state. It is just the final configuration, which means, okay, nothing to be computed. The program is finished. Okay. And now we have the semantics is defined in two steps. Yes, two steps. So first, I define what is a small step. So this is we will see the detail. So this SOS1 means what happened within one step of computation. And once this is defined, we will see that the full semantics is here. It's just by saying, okay, I will repeat small steps. So let us look at this one, which is the simplest. So first, I could just stop. So it means, what is the meaning? The meaning of this says that starting from this configuration, after a number of small steps, I can get this configuration. It's not necessarily a final configuration, that's the point, okay? I want to consider any intermediate configuration which are reached during an execution. So it is an initial configuration and some configuration in the future, okay? So I can stop at any point. I say, okay, let's say that from this configuration, I get the same configuration with no step, with no computation step, or this is a kind of transitive step. Or okay, we could use kind of transitive closure, but okay, this is the following, saying that if within one step I start from instruction 1 and I get the second this configuration, okay, beware. These two things together represent a configuration, and more specifically, it represents an intermediate configuration. Okay, so it is not a final. It is not a final. You see that from SOS1. SOS1 cannot start from a final configuration. SOS1 can work only if I have some program to execute. Okay, so if my configuration says I have some program in my pocket and some state, some initial state, then I will go to this time I don't know. Maybe I could go either in another complicated configuration with a program or to a final configuration. Whatever the configuration, then I will repeat the SOS. So it says that if from C2 I can go to the final step, and if from this specific configuration not finished, I can go to C2, okay, then at the end, I say that I can go from this intermediate configuration to C3. Okay, well, one possible way, it can be formalized using only C1, C2, but okay, this way things are more okay. Well, technically, it can be interesting to consider this way of formalizing things. But okay. Now, what is one step? One step. Okay, steps. So the first, for instance, so I will make a case analysis on the instruction here. Okay, I will see the different possible cases for this one. So if this one is a skip, okay, so it means that I have a program which just says skip. So this program starts from the state. I say, okay, but now there is no program to be run after. I go to a final configuration. For assignment, okay, I chose this way as well to say that, okay, if I have an assign to perform, then I just compute the state as usual. So I update the state using so I evaluate the expression A, I get the result, and I put the result at the right place of the state. Okay, this returns a full state, and I said, okay, and now I'm finished. My problem was very simple, just an assignment. So I run the assignment, and after that, it's finished. I am in a final configuration. Before going to this one, which is complicated, a remark. Here you see that the evaluation just returns a result, because I consider that in this language, I have pure expressions. Now, if you consider languages such as the C language, when you evaluate an expression, the state can change. You can have expression like x++ times blah, 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 and that, okay, this kind of thing. so it is impure, and in that case, it can be interesting to say, oh, actually, computing expression is something which could not know abort or whatever. Okay, so it could be interesting to have small steps inside the evaluation of an expression. So for simplicity, I did not make this choice here, but okay, see, it is okay. When you go to a realistic language such as a C language, the small steps actually is already present in the evaluation of the expression. But technically, it's still the same thing. It just means that okay, instead of using the functional semantics here, I will just say, okay, at this stage, I will, perform the computation small steps by small step, and maybe at the end, the evaluation is finished, and and moreover, I will return a result. So, okay, so I will have something which returns not only the configuration, but also a result of the evaluation. Okay. So now, the sequence is complicated. I will see that later. Let us consider the if then else. The if then else. What is so now? I want to say what is a small step for this instruction here. So as usual, I will compute the value the expression B, and if it is true, the result is true, then I will go into a new configuration which says that now my next program will be the then branch, and the state didn't change. Okay, because evaluating a Boolean expression is pure math language. Again, if evaluation expression change the state, in that case, this semantics would produce a new state, and in that case, I would say, okay, my next program is I1, and the state I get here is the one I got after the evaluation. Okay, so in a way here you see that it is different with these two cases. Here, my new configuration was a final one. Here, my new configuration is an intermediate configuration, saying that, okay, I go to the then branch. Here, I go to the else branch. Okay, let us see the while. The while says that, okay, if I evaluate the condition to false, then the next program will be what follows. Sorry, yes. No, sorry. It is if. No. I want to read this one. Yes. Okay. This one. Okay. So this one is written in an interesting way. It says that, okay, so I meet a while loop, and what I say in that case, okay, I keep the same state S. Okay, my new configuration will consider the same state, but now the program. So I have a new intermediate configuration with a new program which says that, okay, my new program will be this one. If B, then sequence between the body of the loop and the full loop, or not or, I mean the else branch of the if is just skip. So if B, body followed by restart from the beginning. So this is then else skip. Okay, so you see that I just it is a way of representing with AST. You can see that as a kind of a program counter actually. Okay, so I have something and I make a new. Okay, you could see that as some piece of code, and once I am in this piece of code, okay, you can see this configuration. the instruction part of the configuration, like a kind of a program counter inside the AST. Okay, one way of seeing things. Okay, let us go now to the most difficult part of the small steps, which is here. So I say that now I have these to be executed in one step. So what is the new configuration after one step of I1 followed by I2? Actually, so and same here. So actually I have two rules. The two rules consider what happens with I1. So first case, so I execute a small step in I1. I execute a small step in I1 here. And first case, I get a final state. For instance, I1 was just a skip or an assignment. In that case, I say that the next program, the next configuration will start with the second part of the sequence. Okay, so I1 is finished. Now I continue with I2 and with the new state I got here. Now, if I1 cannot finish in one step, it means that if I1 after one step returns an intermediate configuration, then the new program to be considered will be what the how to say the continuation of I prime, which is the continuation of I1, which is I prime, followed by I2. Okay, so imagine I1, which is blah 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 blah, followed by I2, which is blah 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 blah. Okay, so I do the first part of the blah 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 of I1, and then I restart from the point I got here. Okay. Okay, so this is that's all. So we could define our small steps. We can repeat them, and we can play. Okay, so as usual, okay, I defined okay some constants. Okay, what do I define else? Okay, so my preferred square program. Okay, so same as before. I have so it's easier to read it in a textual form here. While I is not equal to n, then I increment I, then x is incremented by y, and y is incremented by 2. Okay, and you have this invariant saying okay. So I have now this my program as before, this one as before, and this new, which forever runs the body of the square. Okay, so this is why true do the same. Okay, let us play with piece 2 square. Okay, first round. So just to see what happens. Can you read here? No, sorry. This one. Okay, so unfortunately, I need to. Okay, we can have it. Okay, so my goal here. So I don't intend to say that I am able to reach any final state. I just say that from state 0, 0, 1, so x is 0, and okay, I remember this should be the square here. This should be 2 times plus 1. So this is value. Okay, so from this state here, after a number of steps, I am able to reach this state. So even this statement makes no sense with the big step semantics. Okay. So it means that I will go back to the same program here, but with 1, 1, and 3. So you can guess that here it means that actually I performed one round of the loop. After one round, so the full loop, I executed the full loop. And after one round, so this one was incremented by 1. This one was incremented by this value, which is 1. And the last one, and this one, has been incremented by 2. Okay, so this is exactly, you see what will happen. Okay. Okay, so I have to prove SOS of this. So SOS, you remember, SOS is repeat the small steps. So, and if I don't, when I am tired, so I say, okay, I will stop the computation, I will have a break and go to lunch. But not now, we will still have half an hour. So I can do that only if SOS has the same configuration here and there, which is not the case at present. So I am forced to continue. Okay. So let us say I will use SOS again. And okay, so let us see. No. It's interesting to have this one here. Okay. Okay, so I just say that, okay, I will use this rule. I say, okay, I will perform one small step and then continue. Okay, and you see that this one has many things are fixed by the shape here. So the initial state, the last state, and the this thing. So I1 is a p square 2. Okay, for this one, okay. Okay, this one should be in C3. Okay, we'll see if we are able to have C3 in this shape. But what we don't have is the intermediate configuration C2. Okay, I have the initial configuration, I have the last configuration, but I don't have the intermediate. This is why I will use my e-apply. I could say also refine with a number of wildcards if you prefer. So I say e-apply, and e-apply we say, okay, okay, we will have to find the C2 at some point. So, okay, so I have two goals. One for the small step, okay, and the small step will expectedly return some configuration, and from this second configuration, I can restart to and have a, okay, try to solve SOS. Okay, so let us solve this goal. We'll use the bracket style for the script, because basically, okay, I want to solve this goal, okay, within two brackets, and then go back to this one. Okay, so you will see that it is better for the presentation. But you can use bullets if you prefer. It's not okay. So what do I say? Okay, so here, okay, it should, okay, it depends on the contents of p square 2. What is p square 2? P square 2, for, hopefully, yes, it is here. Let us keep it here on the top. Okay. So p square 2, you want to try not to touch this one. So p square 2, you see that it is a while something. Okay. So I will use the SOS1 rule for while. This is just obvious. And this one will say, okay, then you continue from this intermediate state, which is just, okay, if condition, then body square, and go back to the while loop. Okay, so it's okay, a little bit long to on the screen, but you just recognize that the while has been translated into an if then else. If condition, then complicated, else just skip. Okay, so okay, we'll try to finish. So here I see that I have an if, so I should probably, sorry, I have a SOS here. Okay, so as it is a SOS, okay, so I will go to the, I will again apply this rule. Okay. what did I, so I did something wrong? Continue SOS. SOS. Goal one is. Oh. I would like to see what goal. SOS. SOS. What happens? This it is an SOS. Sorry. No, it is just a matter. Sorry. What was wrong? It was to remove the thing here. Sorry. I go back to my explanation here. So actually, I finished this call. This is where sorry, I was a little bit tired here. Where is the square here? No, just four here. This is space square 2. Okay, no, this is not. The interesting one is this one. Sorry. Okay, so if you want to understand, just see that. Okay, I said okay, I will make one step here and then continue. Okay, let us start. Okay, sorry, here. And applying my SOS one, I succeed actually. I have finished. By the way, Koch is more clever than me. He says he tells that okay okay I finished to prove this sub goal. So I finished to prove this one. I got my C2. C2 is just this big thing here. Okay. Okay. So I have my so okay. What I have to do is just to close my my brace. Okay, no, that's finished. Okay. Now, what I typed was correct, but at this place. Now again, I will use the SOS again. Okay, let us start with the brace. This time, what do I have? We have a SOS one. We're starting with a if. Bad news, I have two rules for if. I have if true and if false. So, okay, so but we guess that probably, actually we can compute to see what happens. Okay, so I have this, so they are called like this. So what I have to do is to compute this thing to know what happens. So actually I am like in a debugger. I am running the program step by step, and here I am in front of a if statement and have this thing to compute. Okay, so let us see. So let us compute. Like this, I think, compute. So I should say eval b. What's the first argument of eval b? It is a state, maybe. So the state is 0, 0, 1. I don't remember in which order it is. Okay. Okay. Let us try, otherwise it is the other order. You think the other? Eval something in the state. I think no, eval in a state. I don't remember. Okay, well, let us try. No, B not like this. But it is horrible. Yeah. B not and compute. Voilà. And I have this thing. Okay. Okay, so it is the other, sorry. Okay. Okay, so the result is true. So let us choose, okay, randomly the SOS1, blah, blah, blah. So I don't know, so apply SOS1, what, if true, something like this. Let's try. Yes. Okay, and the rule just says, okay, just check that this evaluation sounds true. Okay, well, okay, reflexivity, we know. I can do CBN, sorry. Okay, I finished. Okay, so I enter in the then part of the if. Okay. Okay. Now I have, we have to look a little bit. I have to, okay, an intermediate state. Okay. And now I have a sequence. The difficult one. I have a sequence between body square, which is itself, so here, and a while. So the body square, you remember, it is a sequence of two assignments. Okay, so it is a sequence of a sequence and something. So okay, so remember, it depends on okay. This is always the part where I could make a mistake, because okay, we have a choice between two possible rules for the sequence. The one saying I will have some, so I have to guess if the body square will finish directly or not. Well, we can guess that it will not finish. Okay, so I think I should use the first one. So I forgot the name. We will see. Okay, it is sec F when I'm finished, and the other one is sec I. Okay, so I will use this one. Oh. Okay. No, sorry. I was too fast. It is a SOS. So first, of course, apply SOS again. Sorry. So, okay, finished. So this is a SOS. And before going to the small step, let us say, I still want to work. It is not time to lunch. Okay. So now I have my, I open my first step. Okay. Okay. Here I choose the SON. I hope nothing wrong. Okay, that's okay. Well, at least it may be okay. It depends if I am really able. I will be sure that I am correct. I'm right only if I am able to execute this program from this state and get a configuration which is an intermediate configuration. So okay, so we have to okay. And so SON. So here we see that it is not finished. I cannot close my. I cannot close. If I try, Coq will complain. Okay, so I'm not finished. I should I should see what is in this body square. So body square is an assignment followed by an assignment, remember, okay? So I guess that I should again do this one because I think it will not be finished within one step. So I guess. Okay. Maybe I am wrong here because actually you see the first, here I see the first part of the sequence, and this first part is an incrementation. And this incrementation will just change one value of actual, but it is an update. Okay. Let us print ink I. It is sorry. It is an assignment. It is an assignment, and you remember that the assignment finished in one step. So I will not get an internal. I will get a final state. So here I will have to backtrack, but let us try anyway to apply SOS1 assignment. What's the name? SON1 assign SON. No. SOS like this. SOS1 assign. Okay. So I guess that Coq will complain because we should have here a final state, but I made the wrong choice here. Let us try. Yes, unable to unify, blah, blah, blah. Okay, so I guess that, okay. So here you have to look what happened, but basically this final with inter are not compatible. Okay, so let us go back to this one. Okay, here I claim that using this instruction, I can go to some final state, and yes. So now I can apply. Youpi, I got my, I finished my goal. Maybe, okay, so that's reasonable to put this within one line. Okay, so I finished the first part of my then branch. So by the way, here we see the full goal, we see the full code, the sequence. So here we are left with another incrementation. Actually, what we performed was the incrementation of I. Now we still have the incrementation of X and the incrementation of Y. And then we will have to restart from the beginning of the loop. Okay? Okay, SOS, so as usual. Okay, what I will do. Okay. I put many of them in advance. Okay. So let us go back to this place. So here, I have an SOS. Okay, time to work. Okay. So now I have a sequence made of a sequence. No. Well, I think here I think we should again try this one. Looks reasonable. Okay. One thing that I could do before that, yes, because okay, I didn't pay attention, but you see that the state we have here is written in a complicated way. It says that it is the state that we get after updating the initial state with this okay, in this way. At the left hand, the left value of I is evaluation of blah blah blah. It's better to compute this one. Okay, so let us CBN just to have something which is clear. This comes from the execution. Okay, now we see that the state is easier to read. 101. Okay, we see, actually what we see is the state of the memory after the incrementation of I. Okay, I0I. Okay, it's a funny debugger written in Coq. Okay, so now, so we see something which is easy to see. So a sequence of, once again, I think that this one should probably, I think we should try this one. Okay, let us just copy paste this step by step. Yes, again, an incrementation, so an assignment. Okay, Okay. Okay, and okay. Let's apply SOS again. Let me see. Maybe it is a good idea here to put the CBN here. See better. Okay. CBN. Okay, so I see my intermediate state. And okay, so actually I will copy paste this one. Okay. So CBN, time to work. And okay, now I have a sequence between a simple incrementation and a big loop. Here, I think we should just go to this one because it is something which will finish within one step. Okay. Yes. And I get, so let us, as usual, execute the assignment. Okay. So basically, the last one here should be incremented by 2. This is the meaning of the incre y that we have here. Okay. Okay, it works. So we don't see the result at the moment, but wait a minute. CBN, yes, we see that our state is 113. Ah, interesting. Because I see that here I have 113 and have 113 at the end. Let me see. Inter p equals 2. Yes, I think that this thing is exactly p squared 2. Okay, so actually, time to lunch. Time to, yes. So it is just apply of SOS stop. I hope it will work. Yes, finished. Okay. Okay, so you see that, okay. So that small step semantics basically means that we are debugging or step by step. Is okay. So it's quite funny. So, okay, so I will not detail the next one. This is basically the same, okay, basically the same kind of script. So I say that what, yes. Actually, it is exactly the same script, but instead of using the p square 2, I use the p square inf. Okay. So I guess that I will not do that step by step, but I guess that just by doing that, it will work. Yes, yes, the evaluation of the, yes, at the beginning it will be a little bit simpler because the loop not need to be evaluated. Okay, but let us just copy paste and change when we need. Okay, proof, please. Okay, I will do it. Okay, using keys is better. Okay. Proof. Okay, so I use so SOS again. It is a while loop. I think that's no problem. Okay, and here, compute. Okay, I don't. Okay, I don't. Okay, I could compute that, but just useless. Okay, yeah, I just should let compute be true actually. Okay, but anyway, I just skip this part. Okay, but I think just use this. Okay, it works. Okay, so let us see. Yes, finished. So you see that the infinite loop works exactly, is able as well to reach this state, this configuration. These exercises are really easy. Okay. And now, okay, so for the rest, I will leave. So it will be your job, your homework. So so you can do this. So saying that from the same initial state, you can reach this one. Okay. So basically, you will copy paste the beginning, but then it's not finished here. Here it's not finished. You still have to again perform the loop once, and after the second loop, the second round, you will get this one. Okay, so nothing difficult. But now we will like to do things in a way more in a more abstract way. So the idea is that we can do a number of steps, a number of small steps, and then consider them in one piece, and then another sequence of small steps. So let us say that from C1, I can get to C2 with a finite number of small steps. Similarly, from C2 to C3, then I have this one. So really, the proof is easy. Okay, so it's easy, but you have to take care maybe to okay. So you should make an induction on this one, and probably keep this one quantified, something like this. Prove this by implication. I think it is the way. Okay, so you will try. And then, so once it is proved, it is interesting because the previous lemma is easier to prove. So how you do proceed? You prove that starting from 113, why not? You can go to 2, 4, 5, okay, and then you can prove. Okay, and also you can also this is something we will do all the time, and then you can say that you can go from this state to this, so from this configuration, sorry, to this one. So this is easy. It's just using stop, okay, and then you can prove the initial lemma, this one, saying that we can go from 0, 0, 1 to a final state, final configuration like this, just using the S restaurants using this one, and okay, and the second time probably with this one. Okay, so you see it is quite convenient. So very easy lemma, and okay, and then what can you do? You can generalize to and prove. Okay, okay. For this one. Funnily, it is more easy to work with the infinite version of the algorithm. So the point is the following. Okay, so we make just some some lemmas, arithmetic lemmas. Okay, by the way, you have a tactic in Coq for arithmetic. This kind of things which just use addition and multiplication like this can be solved by an automatic tactic which just uses all the lemmas of the some lemmas of the standard library, such as distribution, commutativity, associativity, the basic thing you know for you. Okay, so of course when you are a beginner, there are training exercises for using the library. After some point, you are tired, and you can just say, okay, try to prove it by hand. Okay, sorry, automatically. Okay, you will see Coq includes other automated tactics such as LIA and so on for dealing with arithmetic. Well, okay, so this is not the topic of today. The point is that I want to define this family of states, saying that I have n times n and successor of n plus n. So typically the invariant that I want to see at the beginning of the loop at each round. And so the theorem is the following. It says that if I start from an intermediate configuration of this shape, I can go to another intermediate configuration, but oh no, sorry, I put a final here. Okay. Yes, it is. No, okay, okay. Well, this is the right one for some reason. I can go to this one, but with S here. Okay. Okay. So I can make a round of the body of the loop. Okay. Then yes. So this is something which is a little bit difficult to solve. So okay. So if for okay. At the moment, just admit it. It is a kind of, because this one is basically a kind of recursive use of inversion, if you look in the detail. So, okay, so it's a little bit technical, but anyway, what is interesting, it is its statement. So it says that if actually you can show, you can see, it basically says that SOS behaves a little bit like SOS1 sequence because, yes, if you have an intermediate state here, yes, it is the equivalent of this one, but with SOS instead of SOS1. Okay. Okay, so it just lifts the one step to several steps for this for a sequence. Okay, so okay, it's a little bit technical to prove, but once so the idea is not okay. Not waste too much time with this one. Okay, so it is interesting as a challenge if you want to play with inversions and recursion. Okay, but okay, not but we can use it. Sorry, this is I was talking about this one, and then we can prove that. Yes, okay. So I use it for because okay, this one is easy to prove, and for this one, which is the one I wanted to have from the beginning. So I go from an intermediate to here. Sorry, here to an intermediate with successor. Okay, so because this one can be repeated, I have in some sense some sequence of small steps. So you could say have a middle big step. I'm not going to say followed. Okay, and then using transitivity, you can repeat this kind of thing. Okay. Okay, so just something which is technical but very easy. So sorry. So at the end, what is interesting is this one. Okay, so first one. Okay, so so at the end, you can prove now very easily that I can go. Okay, this is the one I want to see. I can go from initial to final here. So I put it on the top, and then just using not SOS again, but SOS trans. Okay, and in each of the steps, sequence of small steps, I will use a round that was explained before. Okay, so I repeat this, and I think you can run it if I'm not wrong. Okay, etc. So I use transitivity. Okay, so you can play with it as nothing deep. At the end, you finish and you are happy. Okay, so you can now prove this one not with maybe 50 small steps one by one, but you were able to structure a little bit your proof. And what is more interesting is that you can do the same not on the p²2, but on the p²inf. Okay, so you have the same corresponding theorem, so a round of inf, and that's all. And then you can prove that you can go from the initial state to any state of the shape I to times I and the successor, 2 times plus 1. Okay. You have this invariant which holds, and this is interesting because here you can have many steps. This I is not bounded. Okay. So the funny thing is that it is quite easy to prove it using the previous material. And when you want to prove the same thing just for p square, which is this one it is okay, the finite one, which finished after n steps. Then okay, so it is a little bit more complicated. Actually, you run into the same kind of difficulties. Technical. It is not technical about Coq. It is technical about thinking how to prove a theorem using the right induction. So for this one, so I make a number of suggestions. I did not check, but maybe the same trick could be applied for the big step semantics. Anyway, I think I suggest 2 options. Yes, 2 possible tricks. So I have yes. So one possibility is to replace reasoning on less or than equal by an addition. So this is the one. So I have a solution of this shape for the big step semantics. For the other one, I don't know if it works as well, but it is quite funny because here we use no arithmetics at all with arithmetics. Okay, which is to prove a disjunction of 2. You have to weaken the invariant. You say that the invariant. Okay, you can read online. So this is a disjunction. So okay, so up to now I didn't introduce any other connectors except implication. So in Coq, you also have conjunction, you have disjunction, you have exist. Okay. So except in this part, I don't need them. So in the future lectures on Coq, maybe you will define them. Okay, but okay. So it's nothing very difficult. Just happen not to really need them. So I did talk about them. But okay, of course you can do logic in Coq with the usual connectors as well. And okay, so you have the sequence of steps, which are quite funny. So you have okay, in that case, you have even a little bit of training to understand how to use disjunction, but again, it's optional material. Okay, I think we will stop here for today. Okay, so next time, I will finish this. I explain that we can also use a function instead of for the small step. Okay, but nothing difficult here. I will talk a little bit about certified compilation, but in a very simple framework. And we'll also introduce you to a method, and how to apply it here for defining general recursive functions with Coq, which is basically impossible, but using some tricks, we can do something. Okay, so have a good weekend. Do the exercise, the homework, and see you, I think, next Monday.
Yeah. So launch.